Hello everyone, and thank you for attending today's webinar, Beachfront Property, How Edge Clouds Will Drive 5G Era Revenue, sponsored by Juniper Networks. Before we begin, I want to cover a few housekeeping items. On the right-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit your questions to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is also available for download in the green Resource List widget. Towards the end of today's presentation, we'll ask for your feedback. A survey will pop open on your screen and will only take 1 minute to complete. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn the event over to Heavy Reading Senior Analyst Roz Roseborough. Roz?
Great. Thanks, Erin, and thanks everybody for joining us today. As she said, I'm Roz Roseborough. I'm a principal analyst at Heavy Reading, and I cover cloud infrastructure and management for Heavy Reading. And I'm joined today by Mark Rappaport, Senior Product Line Manager for Contrail Software Portfolio at Juniper, and also by Pierre Bichon, Senior Consulting Engineer for Telco Cloud Solutions at Juniper. I'll open with a few slides on operator plans around Edge Cloud, and then I'll turn it over to Mark, who will go into some of the architectural considerations for Edge Cloud. We'll do a poll question, and then we'll hand things over to Pierre, who will discuss Edge Cloud deployment strategies. We'll have time at the end to take your questions, but please do go ahead and submit them as we go along. So first, to set the stage, here are some recent data showing the timeline for communication service providers to deploy service applications at the edge. We see that at the end of last year, a little more than half of the respondents said that they'd have up to 5% of their applications deployed, and 27% said they'd have 6 to 10%. By the end of next year, 20% say they'll have up to 20% of those applications, and a third expect to have 6 to 10% of them. I think the key takeaway here is that CSPs are indeed moving service applications to the edge, but it will happen gradually over a number of years. And what we're looking at here on this chart gives us some insight into the use cases that are driving edge transformation. As we see, virtual CPE is the biggest driver, with 80% of respondents saying that it is driving their edge transformation. Cloud innovation and 5G enterprise mobility were the next biggest drivers, with 2/3 of respondents citing them. Artificial intelligence and machine learning, remote enterprise deployments, and Kubernetes and containers are lesser drivers for now, but are likely to gain importance as the others get deployed. I'm now going to hand it over to Mark to talk about architectures.
All right. Thank you, Ross, for this introduction. Good morning and good afternoon. My name is Mark Rappaport, and I'm a Senior Product Line Manager for Contrail Software, which is Juniper's flagship product for cloud infrastructure, virtual networking, and security. And as I'm sure you already guessed by now, thanks to my accent, I'm French like Pierre. So today I'd like to discuss about what a typical edge cloud architecture looks like and what are some of the key requirements that are necessary to build an edge cloud infrastructure. I think it's good to take a quick step back for a minute and position this edge cloud discussion in the larger context of what have been the major trends in the telco industry, where I'm sure you all remember all the rage was about SDN, NFV, and telco cloud 5 years ago. But now that the dust settled, I think it's fair to say that NFV did not necessarily deliver on all its promises, and I think that the reasons why NFV deployment did not happen to the extent that it was predicted are threefold. First of all, because the nirvana of disaggregating the whole network functions into many separate hardware and software components created a real challenge in terms of selecting, testing, integrating these various components, and this is a well-documented issue. It explains why outside of large tier 1 service providers, most of the production deployments are actually based on single vendors and NFV silos, or at the very least, chunky solutions provided by a single service integrator. The second factor was that most of these components suffered for a long time of some major gaps in terms of lifecycle management automation, which only have been solved quite recently, and that's something Pierre will elaborate during the second part of this webinar. And last but not least, I think the main reason why NFV lost some of its momentum was because it promised that it would deliver significant cost savings by replacing existing physical network function of the telco infrastructure, while in reality, some of these cost savings were difficult to realize. And just to clarify the title of this webinar, we are not here to discuss about real estate investment. These so-called beachfront properties, this is a tagline that was coined last year by our CTO Bikash Kole, when he referred to the fact that Edge Cloud is a huge opportunity for telcos to monetize their unique assets, which are space and power, in these hundreds of thousands of remote cell sites and COs, which are essential to offer the low latency services that will be made possible with 5G. And this new revenue opportunity is basically to provide Edge Cloud infrastructure as a service, aka renting distributed compute to third-party application providers who will run some new real-time services that will leverage the capability of this low latency 5G network. So what's happening right now is a battle between the network operators who can leverage these real estate assets and the main public providers who can leverage that tremendous software experience in building fully automated, scalable, and reliable infrastructure. So let's talk a bit about the architecture. This is a simplified view of what an edge cloud architecture would look like. The idea that it does not start from scratch. It's actually based on a typical NFV stack being enhanced and expanded. And I'm sure that you all recognize all the green boxes on the right side of this slide, which are all the standard building blocks like x86 COTS servers deployed in large data centers for the hardware, NFV infrastructure made of OpenStack for virtual compute, which is de facto standard now, a data center SDN solution like Contrail, software-defined storage like Ceph, and on top of it, the typical VNFs like virtual ETC, virtual firewall, virtual CP, and so on. And above it, the usual Mano-ish layers like ONAP and other orchestration elements. On the left side of the slide, the blue components are the ones that augment traditional NFV to make it more edge suitable. And so on the bottom, it starts with more specialized hardware with smaller size and optimized power consumption that leverages hardware acceleration to provide higher performance in a small footprint. At the NFV infrastructure layer, it's about supporting not just VM, but containerized workloads using typically Kubernetes orchestration, and having an SDN layer really optimized for the edge that can deal with a high number of sites and limited CPU available. That's something I'm going to go into more details in the subsequent slides. And above it, that's where you will have your edge compute applications, whether they are like internal to the telco like vRAN or potentially some third-party application. I also want to highlight that Edge Cloud is a bit of the Wild West so far, as many vendors are coming on the market with their own proprietary edge compute stack. And while it can provide a faster time to market in the short term, it comes with its own challenges for the long term. And this is also something that Pierre will develop in his section of the webinar. Now I'd like to move from the simplified model I just presented to a real example of edge stack, like the one from the Acrano project. And for those of you who are not familiar with Acrano, it's a Linux Foundation project that was started last year by AT&T, NTT, and a number of vendors in the industry, including Juniper, with the objective of building an open source software stack optimized for Edge Cloud. And I'm not going to go through each and every component of this blueprint. It's obviously a pretty busy slide. But I just want to highlight two things here. The first one is that a Acrano project starts from scratch with building a CI/CD tool chain across the entire stack. And this is something really critical that Pierre will develop right after me. And the second thing that I want to highlight is the fact that networking is a bit of an underestimated component in this stack. And that's why I highlighted in the purple box in the center of this stack the network control and network data plane pieces, where, as you can see in the original blueprint, Acrano identified multiple control and data plane implementations to cover the different applications that need networking connectivity, and you get a mix of OVS for traditional VM networking, SR IOV for high-performance workload, Calico for containerized workload. We believe that there is room to optimize this blueprint by replacing these disparate networking components with a unified SDN solution that can cover all the use cases and provide connectivity between these various flavors of VM, container, bare metal workloads, and their different performance requirements. And this single layer is Tungsten Fabric, which is the open source project that is also part of the Linux Foundation, and that is the upstream source code that Contrary is based on, Contrary being our commercial package. Okay, so the five key pillars for an Edge Cloud platform, the key requirement that we think must have, the first one is centralized control to minimize the overhead and optimize the manageability. Second one being supporting a reduced footprint due to the space and power constraints in these small sites and the limited available CPU and memory. The third one is the capacity to support containerized workloads, which allow for an increased density of application and to support more modern cloud-native network functions. The fourth one is the capacity to support network slicing, which is a critical requirement in 5G, especially for multi-tenancy, including of third-party service providers or third-party applications, which is a must to monetize this new 5G network. And the last one is strong security. So now let's review them one by one, starting with centralized control. Okay, so what you see here at the top of the diagram is a typical large data center, which hosts all the compute, storage, networking control components, which are typically deployed across 3 instances for redundancy and scaling purpose. And at the bottom of this diagram, you have two remote POPs. For example, POP 1 on the bottom left, which is a cell site, and POP 2 on the bottom right, which is like a CO. And on each compute node, whether on the centralized site or the remote POPs, you have the software data plane that is part of control, which is the router, the blue icon. Now, there are a few key points that I would like to highlight here. The first one is that control points for the vRouter that are on the remote compute nodes deployed in POP 1 and POP 1 and POP 2 are actually in the central data center. That's represented by the two boxes, POP 1 control and POP 2 control, which are VMs in the regional data center. So basically, there is no need to deploy any control function that would be co-located with the compute nodes in these remote POPs to deal with the limited available resource in these remote POPs. The second point that I want to highlight is that it's possible because of native control and data plane used by Control, which is based on all the standards, BGP and IP and TLS protocol suites. So these protocols are natively used, obviously, in the backhaul and transport network. So the control functions that are hosted in the central regional data center not only control the vRouters that run in every compute node, but they also actively provision the data center gateways or the cell-site gateway, and they stitch the traffic between what's going on inside the data center and what's going over the transport network. And that is the reason why it's basically because you have this full awareness from the control plane of the topology, of the connectivity between, on the top, the regional data center, and at the bottom, the various multiple remote POPs. It's possible to have direct connectivity between, in the example that is illustrated here, a container located on the bottom left in POP 1 with a VM that would be located on the bottom right in the POP 2 without tromboning the traffic through the central data center gateway, even though all the control functions reside in this central data center. Okay, the next key requirement is supporting a reduced footprint. And here there are multiple options which can actually be combined depending on where you sit in the network. So the first one is doing some kind of hardware acceleration offload for the vRouter data plane, where instead of running your entire data plane as a software module in your host operating system, you are leveraging the hardware capabilities of some advanced network interface cards, which are typically called SmartNICs, which typically have either an NPU, a network processor, or an FPGA that can partially or fully run the entire data plane of the router, and that would then allow to reclaim all the CPU cores which would have been used by default by the software implementation. The second way to reduce the overall footprint of your NFV infrastructure in a small site where you don't have many servers would be, instead of having a separate stack or rack of servers that are dedicated for compute, which typically also are running the SDN layer for advanced networking, and another separate stack of servers just for the software storage solution is to use a hyperconverged infrastructure where each server runs compute, storage, and networking. And this would be particularly applicable when you have a small number of servers. A third potential solution to reduce the footprint is using a lightweight version of the router, which uses less CPU cores, which runs on smaller platforms, which are typically ARM-based rather than x86, which are used on large DC servers deployed in the large data centers, with a smaller memory requirement. And the last possible solution is basically to completely remove the hypervisor layer and the software networking layer from the server, and rely entirely on your underlay and top-of-rack switch to implement all the networking capabilities, basically running bare metal workloads. All right, so that was the second key requirement. Let's move to the third one, which is the capacity to support containerized workload. So the reason why containers are particularly well suited for edge cloud environments is the fact that a container has a much smaller CPU and memory tax compared with running a full-blown virtual machine with its own guest operating system. However, running containerized workloads introduces several major challenges in the context of edge cloud. And so the first one that I want to mention is the need to extend service chaining to containers, which is the diagram at the top of the slide. Service chaining is a capability to steer traffic through a set of network functions, which applies some kind of packet processing, like in this example, firewall. And that's something that's been used extensively in NFV for quite some time now. The challenge here is that typically to steer traffic through a VNF, you need at least two separate interfaces to differentiate the traffic coming from one side with the traffic coming from the other side that the network function is applying processing between. So in the example here, you have the north-south firewall, which has one interface facing the end user on the left, and one interface facing the offload virtual network on the right. And specifically, the challenge when you start to use containerized network functions like the east-west firewall here, that sits between the offload virtual network on the left and the backend services virtual network on the right, is that Kubernetes by default only supports one interface. So a key requirement is the capability to support multiple interfaces for a container to be able to use it in a service chain. The second requirement, which is represented at the bottom of this slide, here basically the challenge is to deal with having two separate compute orchestrations, one for virtual machines, so typically OpenStack, and a different one for containers, which would be typically Kubernetes. So the real challenge comes when you run containers inside VMs, which is a very common deployment model. And in a naive implementation, you would have to deal with two stacked SDN instances, one on top of the other, so one taking care of the virtual machine and the other one taking care of the containers. And with the fact that you would have a double encapsulation for the traffic that comes from a container through a virtual machine. Basically, when a packet leaves a pod, it would get a first tunnel encapsulation, and when it leaves the VM to get through the host operating system, it would get a second tunnel encapsulation, which is highly inefficient in terms of processing and packet size, and which also makes it more complex to have connectivity between containers and VMs. So the solution is what we call here Kubernetes nested mode, which is to collapse the two SDN instances into a single control layer that spans across both OpenStack and Kubernetes. And to get rid of the double encapsulation challenge that I just mentioned is to rely on having a single layer of vRouter for the data plane that runs at the host operating system level, or at the hypervisor, basically, and just use native IPVLAN encapsulation to separate the traffic coming from the different pods inside the VM, which is what's represented here. All right, moving to the next key requirement, network slicing, and which is really related with multi-tenancy. Just to wrap up on the container networking, one issue with Kubernetes is that it has a pretty weak isolation model by default, because all the pods are reachable between each other with no traffic separation. And the idea here is to implement isolation between the pods, the minimum being at the namespace level, but also potentially at a more granular level by providing isolation at the service level, aka between different pods of the same namespace. And on the data plane, which is enforced by the router component, the model to implement multi-tenancy is basically the same as the one that has been used forever for IPVPN services, which is having separate routing instances and forwarding tables for each tenant. All right, then moving to the fifth and last requirements that we have identified, centralized security policies and encryption. So the last pillar of this architecture is being able to centrally define security policies that are enforced through the distributed vRouter data plane and compute nodes across the entire spectrum of sites, from all the way from the regional data center on the right to the remote COs and cell sites on the left. Another aspect of providing strong security is the capability to selectively encrypt the traffic where it makes sense. And on this slide, we have two main use cases for that in the context of Edge Cloud. The first one is to encrypt the traffic between a CO and a remote cell site, where this cell site is connected through, for example, a third-party access provider, which is typically a case for, let's say, a small cell. Another use case, a strong requirement for encryption, is to provide secure connectivity to public cloud providers, where you might want to run some compute-intensive workload as part of your edge compute service, like machine learning or analytics. And I believe that's something Pierre will also provide some more content on the public cloud use case in the context of Edge Cloud. Okay, so now that we covered the 5 key requirements of the edge cloud architecture, we have a quick poll for the audience.
Great. Thanks very much, Mark. And yes, here's our first poll question of the day. I'd like to ask the audience what they think is the most critical requirement for the edge cloud. So do you think it is centralized control? Is it a reduced data plane footprint? Is it having containerized workloads, network slicing, strong security, or perhaps it's something else that we don't have listed here? So while we give the audience a minute to answer this, I'd like to ask Mark and Pierre, if you want to chime in, what do you think, or what are your clients indicating to you as the most critical requirement, if you had to pick a single one?
That's a tough question. It's like asking which among your child is the preferred one. I would say that there is not a single answer. It's going to depend on the customer and what is really the key driving use case for the edge cloud deployment. So I'm really curious to see what the audience will answer. And looking, right now we already have like 50 plus answers, and it's really interesting to see the spread across the 5 options.
All right, let's take a look and see what people had to say then.
Okay.
Wow, it looks like it's pretty, I would say, relatively evenly split.
Yes.
Security, about a quarter. Yeah.
Yeah, that's basically the answer on which one is your preferred child. It's quite evenly distributed across these. Yeah, maybe security and reduced data plane footprint have some kind of a higher priority, but it's not like a huge, not by a huge margin.
Right.
Interesting.
Which is about, yeah, I think that's probably what we expected.
Yeah, I would also be curious to know what are the 12% of something else. So if some people believe that there is some key requirement missing here, I would love to get, as part of the Q&A, some questions and comments on what are the other key requirements they believe are needed for edge cloud deployment.
Okay, that's a good idea. We can, why don't folks who said something else, why don't you tell us that in the Q&A? Just in the interest of time, let me throw it over to Pierre so we can start talking about the deployment strategies.
Absolutely. Thank you, Ross. Thank you, Mark. So what I would like to do here is continue what Mark has been telling about how the edge cloud will be built and how they will deploy and what will be the strategies to deploy this cloud. There will be some different ways to do that, and there is a myriad of choices and to be made on the way. First of all, we are in a context of 5G here, and what I wanted to raise here is that the cloud technologies have evolved in parallel to 4G, which quickly leveraged NFV for things like virtual DI-LAN services or virtual EPC, for example. The cloud technologies have matured enough to support telecom functions, and the edge clouds are a simple part of this evolution, as we see here. So on its side, 5G has been designed to leverage cloud technologies, and over time, the whole infrastructure of 5G will be built over clouds. However, today, when 5G will first deploy, meaning namely this year in 2019, 5G can benefit from edge cloud from day one, as soon as a new radio is available and is deployed. Reason is things like enhanced mobile broadband, plus, that's my own terminology here, meaning higher throughput compared to 4G. And also fixed wireless access creates a big surge in traffic volumes. And the distribution of content and applications toward the edge will be a solution to avoid to have all the traffic thrown away into the core of the network, and eventually only happen to go to the internet. And second, 5G will introduce low latency features, but just in a second phase. However, applications such as the one that Mark was mentioning, like machine learning-based image processing for services like augmented reality or connected vehicles, they can benefit also from day one from the low latency offered by just having higher speeds. Right, so these services will be, of course, best located when they are close to the end user, meaning that they will be located in an edge cloud, which happens to be ready as a technology today, along with the other useful cloud technologies, such as container support, like Mark was saying, which is mentioned cloud native here, multi-cloud, etc. Right. So the edge cloud will deploy in different phases, and what we have seen in the last few years is that NAV has started to be deployed in a centralized mode in just a few sites. That's where the virtualization of network platforms have been maturing, and the requirement to have further distribution is driven really by the efficiency of the infrastructure of the telcos, to be more efficient for virtualizing the EPC, for example, or virtualizing the firewalls or virtual CDNs or virtual IMS, notably to prepare for the 5G traffic growth I was mentioning. So in the short term, this is limited to a distribution to more sites, like tens or potentially hundreds of sites, depending on the country, of course. And edge cloud sites will see the distribution of the virtualized platforms, as we see here, OpenStack, Kubernetes for VMs, containers, also bare metal servers, storage, many flavors of hardware, like Mark was mentioning, GPUs, FPGAs, hyperconverged servers, ARM processors, fungible platforms, etc. Under that also will be distributed the underlying IP fabric made of switches, which physically connects the servers together. And finally, an SDN layer to glue all that together. On top of that, of course, you need to deploy the VNFs, virtual PC, for example, caching, and not to forget the end user applications, which will be designed to use edge clouds, right? So distributing all that in potentially hundreds, thousands of locations require special attention, and this is what we are going to quickly view here, because what happened and what we have seen after the few years of field experience of deploying NAV is that, first of all, the integration of virtualized systems can be complex. It requires skills in both cloud technologies and also in networking. The integration in-house is very time-consuming, meaning that it could take you to delay deployments and lead to too late time to market for the services which should be offered through edge clouds. As a consequence of this experience that we have seen in the last few years, we see emerging three ways to consume NAV. First is self-integration, taking NAV components as Lego blocks and assembling them in-house. Right, first way to do things. Second is outsourced integration, where a third party builds, operates, and transfer to the service provider. And this may be a complete outsourcing or just a partial outsourcing, depending on the model which is chosen. And the third way is to consume as a service, offered by cloud as well as service providers. Right? We have seen also that deployments of an NAVI, the NAV structure over a solid SDN layer, such as Contrail, of course, have been more successful than without any SDN stack. And we have seen that deployments of a common horizontal NAVI stack on top of which VNFs are deployed have been more successful typically than deployments where each VNF has its own stack, NAVI stack, which leads to a huge complexity of operations and cost because you multiply the number of NAVI stacks and VNFs for each VNF. So in this context of experience that we have acquired, what about edge cloud, right? How do we deploy edge clouds in a complex environment like this with different ways to do that? Well, so the edge clouds simply only increase the challenges that we have seen. Something needs to be done to better succeed in an edge cloud deployment, and the light comes from automation technologies. They are, but not simply automation, right? We've been talking about automation for some time already and applied to networking as well. And it's been already used in cloud deployments, but it's mainly been based on scripting, even if this is nowadays a very evolved flavors of scripting. It's still better than manually, but still not efficient enough for edge clouds. Again, the scale is very different. The focus also has been first made on automation of deployment, right? But it's not enough. Telco clouds have a life cycle to be managed, and applications leveraging those clouds also do have a life cycle to be managed. So it's not only just for the deployment. And software development technologies now come to the rescue for this and start to be applied for telco cloud lifecycle management. Technologies around DevOps, which is a methodology framework for development of applications and also for its operations, is being introduced, and it's been also accompanied with tools to perform continuously the integration, meaning develop code or network features, network capabilities features, network services, build and test it, test this code, and then deliver, meaning deploy this code and then monitor it live. Right? So this methodology and all those tools, which are mentioned here just as examples, can be leveraged not only for the applications, which will sit on top of the edge clouds, but also to automate the edge clouds themselves, right, at a large scale. Just an example, it would be possible for to test automatically and upgrade just one component of the NAV stack, or even just a simple function of this component, without waiting for 3 months to test it and have a maintenance window. You could do this upgrade just almost daily if you want it, right? As soon as the code is ready, right? So it's a new way of thinking how we build networks where the deployment is automated, meaning that configurations are created and deployed automatically. The network is monitored continuously so that issues can be identified as quickly as possible and corrected. And ultimately, the cloud infrastructure is considered as a code where any change is tested and validated before being put into production live. Right. So how does it apply to edge clouds? Well, CI/CD can greatly help to manage the scale and complexity of very distributed edge clouds. The edge cloud infrastructure can be built upon a clean stack, as depicted here. First, you have an SDN-enabled NAVI, supporting the edge cloud and multi-cloud and slicing capabilities, right? On top of that, you have these VNF layers, this VNF layer, then the platforms with APIs so that applications can consume this stack, right? And applications will be sitting on top of that. And you end up having 2 layers, but each one benefiting from its own CI/CD environment. So it's critical to be able to build edge clouds this way. Otherwise, the complexity will be too big. They will be very hard to maintain. In fact, for edge clouds, it's the right moment to move ahead towards self-driving networks, and this could be the opportunity for doing so. Edge clouds by themselves breed new opportunities in terms of deployment and business models. So we'll see developing new ways to offer services when edge clouds are offered. It will be possible to distribute all the telco services. The green picture on the top left that I was explaining at the beginning. This includes edge cloud as a service, for example, be it edge cloud infrastructure as a service, or edge cloud as a platform, or even edge cloud as a bare metal service, or multi-cloud as a service. So telco services can be distributed down to the edge sites, but also private clouds, which will extend some of their applications down to the edge locations where they can really leverage the low latency capabilities, for example. And then even public clouds can be located at those edge locations, or at least some part of those public cloud applications and services. So this will drive new business model opportunities, such as things like the telco can run all the functions and services in each edge cloud real estate, and some functions or services in a public cloud. Also things like the cloud or over-the-top provider collocates its platform in the telco site or consume the edge cloud as a service from the telco as an offer. And last possibility is that the enterprise consumes edge cloud as a service from the telco, collocates application there, and consumes cloud or OTT functions from within the telco real estate itself. Right. So those combinations will require a high degree of flexibility, and beyond a very critical networking layer, the automation of the lifecycle management will be critical. Otherwise, it will be way too complicated to be flexible enough to deploy all those business models. So note that I didn't include so far security and analytics, just to keep it simple. But obviously, I mean, those two dimensions need to be added. Right? Let's take two examples to illustrate all that. The first is smart cities, where multi-tenancy is really very critical by nature, as many entities consume services from offered by many verticals, and those verticals include also service providers of all kinds. New technologies which leverage 5G, IoT, or machine learning will make good use of edge cloud in smart cities. We have many examples in the press nowadays. For example, a facial recognition where a machine learning engine can pre-process video streams at an edge site equipped with powerful GPUs to offload this intense processing from the, for example, the video cameras. That will be something that will be deployed easily in edge cloud. So here, multiple cloud consumption scenarios will be possible, just as the one I listed before, which are mentioned here, but also any other model in the future. And another example could be connected vehicles, where it's also very similar with multiple tenants, which will likely to leverage edge clouds. For example, an insurance company who wants to increase safety, so to provide safety services to their customers through onboard video analytics, where again a machine learning engine located at the edge of the cloud with very powerful GPUs can process video images just to detect risks on the road and prevent an accident before and warn the driver, or just tell the car directly when it's a semi-automated car. So again, here, a combination of private, public, and telco clouds can be offered as a service at the edge, and all those combinations can happen. Right. So many models, a lot of flexibility, and it would be nice to have your view on how this can be organized and what you think you can operate your edge cloud. And maybe Ross, you can lead us to the poll, right?
Right. Great. Yes. Thanks, Pierre. Yes, our last poll question of the morning is, which model do you plan to use to leverage DevOps for your edge cloud? So the options are, will you do it in-house and build, meaning that you will build and operate it yourself? Will you do a partial outsource in the build, operate, transfer model? Will you do a full turnkey outsource to a systems integrator? Or perhaps you have no plans to shift to DevOps for the edge cloud. And just like we did for the last one, we'll give folks a couple minutes, or a couple seconds, I should say, to answer the question. And again, I will throw it out to Pierre, and if Mark, you want to chime in too. Again, which do you expect to see given your conversations with customers and potential customers about how they're going to move forward on DevOps? I guess I'll start with you, Pierre, since you just brought us into this point.
Yes. Well, it's a very active conversation that we are having today. Our customers who were first deploying NFV themselves for just centralized deployments, they have seen all the difficulties to do the integration. They have acquired a lot of expertise in the process, and it has been pretty long, right? So even those service providers who have done that road are thinking now again how they should go ahead, move ahead, right? And many of them are investigating different ways, as I was explaining. So it's moving. It's not like one path is chosen, but it's evolving over time. So probably it's going to be an evolution over time where service providers will embrace outsourcing in some way, partial or complete. And it may take a bit more time to see them consuming services, the edge clouds as a service, but that's certainly something that they are thinking about. That's what we've seen.
Okay, thanks for that. So let's take a look and see. We've got, you suspected it would be outsourced, but a decent amount saying they're going to do it in-house. 43% said partial outsource with a build, operate, transfer. 21% with the full turnkey. And about the same number saying they'll do it in-house. And 16%, which is probably about right given some of what I've seen in some of my past surveys. Not everybody's ready to go to DevOps yet. That's fine. Again, let me just go ahead and hand it back over. I believe Mark is going to do the first part of the summary here, and then we'll have a little bit of time to take some questions. So I'll hand it back over to Mark right now.
Thank you, Ross. So for the key takeaways, we'd like you to keep in mind, the first one is that networking is both one of the most overlooked pieces and at the same time a crucial component for successful edge cloud, as hopefully you've seen when I covered the various key requirements for an edge cloud architecture. Many critically touch the networking part of the stack. And the second one is that I just want to repeat again that the major difference between NFV version 1 versus this new iteration, which is focusing on edge cloud, is the capability to provide services to third-party application providers. That's really the revenue opportunity. And being able to support the different models that Pierre covered in his part of the presentation is key. It has to be part from day one of your reference stack if you want to make it viable.
And I wanted to add a couple of points to what you said, Mark, is that, as I was saying, edge clouds are complex systems and will likely be deployed using a high degree of automations or at the risk of not being deployed at all. At least, I mean, that's a straight statement, but at least that's our opinion, that this kind of automation is absolutely required when you deploy large scales of clouds like edge clouds. And also, successful edge cloud deployments will require this combination of private, public, and telco clouds, because that's the combination that will make it the most efficient, the most rich to deliver plenty of different services and be flexible enough. So that's something that will be a key requirement. And of course, networking in that context is critical, as well as security. But security will be for another webinar.
Okay, well, thanks very much both for all that. It's quite a bit of information. We have a little bit of time for questions, so we'll take a few of them here. And for those of you whose questions we didn't get to, we'll be able to follow up with you after the webinar is complete. So let me take a few of them here. Okay, first one here. You say edge cloud will be deployed in steps, going from centralized data center all the way to the tower access. So wouldn't this be too expensive instead of deploying directly at the edge or the cell tower access?
Well, if I can, you want to take it, Pierre? Or
no, go ahead.
Okay, so I would say you get the typical 80-20 rule that is going to apply here again, meaning that 80% of your cost is going to be on the core. 80% of the cost is going to be at the access, and 20% of the cost is going to be on the core. So deploying these capabilities on the central data centers and metro POPs will have a marginal impact on the cost just because of the number of sites, compared with the cost of deploying these capabilities on the thousands or tens of thousands of remote COs and cell sites. I don't know if you want to add something on this, yeah.
No, you answered to the point. Just to add that the operations, the way to when you want to deploy at a large scale, I mean, you need to really plan it carefully and doing deployments at the right, maybe in specific locations or areas or for a specific service could be a way to do that gradually and gain the experience or gain at least to see the benefits and be able to correct things really quickly, in fact, rather quickly.
Okay, thanks for that, both. Next question is centralized control mode of deployment available today in tungsten fabric?
Okay, so that's a pretty product-loaded question, and the answer is yes. So centralized control mode is a capability that was introduced some time ago in the product that we called internally remote compute. And that's something we started to work on quite a while ago for a European customer, even before edge compute started to become a key application and use case for this. So the bottom line is that yes, it's supported. Having said that, to be completely fair, you need the same level of distributed capabilities in the other components of the stack, like obviously compute and storage. And we know that for OpenStack, there has been a number of recent evolutions in deployment to support that, basically around Nova, and having like a centralized component to manage the life cycle of the different compute nodes. in the case of storage, I think this is a bit trailing behind the rest. So it's going to come in the future, and it's going to be enhanced over multiple releases.
Okay, thank you. Want to remind folks to please take a minute when we're done to do the survey. I should have got the URL out there for you guys to click on. And wanted to do for our last question, there's a couple questions here about latency. Actually, someone had said that latency was one of those, the most important requirement for the Edge Cloud. Then we have a couple questions about it, so we can probably handle them both together. One just asked if we can address the delay requirements and backhauling constraints for the Edge Cloud. And like I said, someone else just said, isn't reduced latency the key benefit of edge computing? So I think perhaps, Mark, you can talk a little bit about that maybe.
Sure. I would say that's true. Latency is both a requirement and a key benefit of 5G and Edge Cloud. And it has some impact on the architecture itself, meaning that obviously you need to distribute deep inside your access network these compute nodes to cope with the latency constraints. I think it's also to some extent covered, at least partially, with the reduced footprint model that I presented, like using, for example, hardware offload for a data plane is also a way to cut on the latency that would be introduced otherwise by doing pure software forwarding. I don't know if you want to add something, Pierre, on the latency. I know that's a topic you know quite well.
Well, in fact, it's also a balance of how low you want the latency for your applications, and meaning that how far you want to distribute your workloads compared to how much it costs. I mean, we had a question on cost as well, and this is a balance, right? So latency, yes, it is, and today it is very mixed. You need to have a strong benefit from doing, I mean, service revenue benefits to do this support with very short latencies. And we see that there is a balance today where some services can easily be deployed within the range of below 20 milliseconds of latency between the application and the end user. And this could be, that's an average, between 5 and 20, let's say. And when you consider lower latencies, that's where, in fact, the future capabilities of 5G will be important, because then on the air interface you will be able to reduce your latency, so that in that case you also can reduce latency on the backhaul where the workloads will be located, so you can distribute further your workloads to go to very, very low figures, like just a few milliseconds of latency, which will be key for really high touch low latency services, what has been called the tactile internet, so very, very interactive services. So, it's, today people are a bit waiting for this second step and planning that carefully, because it is relatively costly, and you need to have the applications and also support from the 5G radio as well.
Great. Well, thanks very much. That was a lot of really good information presented there, and I hope it was useful for everybody on the call. So we're going to go ahead and wrap it up. So I'd like to thank everybody for your time today, and thanks especially to Mark and Pierre, and hope that everybody has a good rest of your day. Thanks.
Thank you very much.
Thank you.